For years, battery manufacturers have relied on mechanical cutting to slice lithium-ion electrodes to size. But physical blades drag against the material. This friction leads to rapid tool wear and causes severe mechanical deformation along the cut edge. Laser processing solves the friction problem. Manufacturers can use high-speed, continuous wave thermal energy to slice through the material precisely, without ever making physical contact. But lasers introduce a new failure point: heat. The intense thermal energy required to sever the metal often vaporizes the critical active material near the edge of the cut. To understand where this damage occurs, we have to look at the anatomy of a lithium iron phosphate, or LFP, electrode. It consists of an aluminum current collector foil sandwiched tightly between two layers of active material. When the laser slices through the sandwich, any uncalibrated thermal energy destroys that active coating. Losing that material directly reduces the energy density of the finished battery cell. To optimize this cut, researchers track a primary independent variable: volume energy. This is a combined metric derived from the laser's power output and its scanning speed across the material. The physical properties of the electrode itself also matter. We have to account for the thickness of the active material coating, alongside its calendering, or compression rate. We evaluate the quality of the cut using two specific metrics. The first is the kerf width, the physical gap where the aluminum current collector is entirely removed by the laser. The second is the top width, the wider zone bordering the kerf where heat has stripped away the active material, leaving the underlying foil intact. The physical difference between these two measurements is the clearance width. It dictates the exact amount of wasted active material along the cut edge. The physical configuration of the electrode dictates how heat moves through it. Controlling that thermal physics minimizes material loss, which ultimately determines the battery's true capacity. This chart maps volume energy versus cut widths for standard uncompressed electrodes. As energy increases, widths grow logarithmically, but thickness alters trajectory. Between the 47 and 90 micrometer samples, the gap between top and kerf width is much narrower for the thicker electrode, controlling clearance width. When working with standard uncompressed manufacturing lines, adding thickness to the electrode is a reliable way to control active material loss. Introducing the calendering process, this chart overlays 36 and 76 micrometer compressed electrode data onto our baseline. Across all volume energies, compressed electrodes produce significantly narrower top widths. That density demands power, requiring a much higher volume energy threshold just to establish a kerf width. Compressing the material mechanically alters how it reacts to thermal energy. The denser structure physically limits the heat-affected zone, protecting the surrounding active material. To understand why compression restricts the damage, we have to look at the microscopic lattice structure of the active material. In a standard porous electrode, air gaps act as thermal insulators. Laser heat pools at the surface, destroying the top layer. Calendering forces particles together, increasing thermal conductivity. Instead of pooling, the tightly packed matrix rapidly channels the heat downward. Lower porosity means more material is packed into the exact same volume. It takes a much higher amount of total energy to vaporize that mass. The compressed lattice essentially operates as a highly efficient heat sink. It diffuses the thermal load rapidly, suppressing the localized surface vaporization. We can observe the physical evidence of these thermal dynamics by examining the actual cut-edge morphologies under an electron microscope. There is a specific thermodynamic window where the laser forms perfectly uniform kerf and top widths. Researchers identify this as the proper cutting region. If the volume energy exceeds the electrode's ability to diffuse the heat, the cut hits the excessive cutting failure state. The aluminum current collector melts unevenly, re-solidifying into jagged, irregular edges. The exact parameters for that proper cutting region are not static. The optimal window shifts entirely depending on whether the electrode is compressed. Generating a clean cut requires calibrating the volume energy directly to the structural density and thickness of the specific electrode. Manufacturing a clean edge is only part of the equation. We have to track how these structural decisions impact the long-term electrochemical performance of the cell over multiple charge cycles. This chart plots specific capacity, measuring charge storage per unit mass over 20 cycles. Counterintuitively, the uncompressed electrodes retain a slightly higher charge per gram. At the end of 20 cycles, the uncompressed samples hold at 150 milliamp hours per gram. The compressed samples fall lower to 143. This is the penalty of density. Calendaring reduces the electrode's porosity to around 72%. This physically narrows the pathways required for lithium-ion diffusion, slowing the transport kinetics inside the battery. Optimizing the physical density for the manufacturing laser actually creates a bottleneck for the internal chemistry of the final product. But specific capacity only measures charge relative to mass. For real-world device performance, the decisive metric is areal capacity, the total charge storage available per physical unit of area. Because the calendaring process packs the active material tightly together, compressed electrodes begin with a higher initial mass loading. You are fitting more chemically active material into the exact same spatial footprint. We also have to account for the amount of material removal during manufacturing. As this chart shows, compressed electrodes suffer far less active material loss when subjected to identical laser energies. When you measure the final cells, the compressed electrodes achieve a higher overall areal capacity, 0.64 milliamp-hours per square centimeter, compared to 0.62 for the uncompressed baseline. The math scales in favor of density. The higher initial mass loading, protected by a highly thermally conductive lattice during the laser cut, mathematically overpowers the slight penalty in internal ion mobility. The mechanical compression of the lattice dictates the thermal physics of the laser. By designing the structure to diffuse heat efficiently, manufacturers can limit surface damage and maximize the true capacity of the finished cell.